Hello, this is Brian Washburn. I'd like to give an introduction to nonlinear oscillations and chaos. Okay. So far in class, we've looked at a linear restoring term, and we've looked at it under a couple different conditions. We looked at simple harmonic motion. We looked at linear restoring force with a dampening term, and also we looked at driven systems with a linear restoring force and also some dampening term. So now what I'd like to do is specifically look at nonlinear oscillators and the route to chaos. Okay, so to start off, let's talk about what is nonlinear about nonlinear oscillations. Well, it's the restoring force. The restoring force is nonlinear. And a good example is that of a simple pendulum. The restoring force is a component due to gravity, so it's equal to mg sine phi, where phi is the angle it makes with the vertical. First of all, the force is restoring because there's a minus sign, so it causes the angle phi to go small, or go towards zero, I should say. And then the functional form depends on sine of phi, so that's a nonlinear function. Okay, so that's a nonlinear restoring force. Now, in general, if I have any type of restoring force, I, in principle, can expand this in a Taylor series. Here's an example of a Taylor series where the equilibrium position is equal to zero. There will be a first order term, a minus, and that is a linear term or a linear restoring force. That's Hooke's law, and this gives rise to simple harmonic motion. But if the stretch becomes large and these coefficients are of a specific size, then we may need to include these nonlinear terms, x squared and x cubed, in our force. And these are called anharmonic, okay, meaning that the solutions for this type of restoring force are not harmonic functions. And in general, we cannot come up with an analytic solution, okay, for that particular differential equation. We have to use a computer to solve, okay. So what's nonlinear about nonlinear oscillations? The restoring force is nonlinear. Now, let's talk a little bit about properties of nonlinear motion. There's a few, and I just wrote two of them here. One thing that's associated with nonlinear motion is that the motion can be periodic, meaning it repeats. But that period, you may have one period, or you might even have multiple periods. And here I kind of sketched what a multiple period. Notice it goes high, high, low, low, high, high, low, low. Okay, and so then you notice there's actually two periods here. There's a period from the high peak to the low peak, and there's another period from the high peak to the high peak. So that's what I would call period 2, okay? And so you could have multiple. You could have period 2, period 4, such and such. So that's a property of nonlinear motion, okay? A second property of nonlinear motion is that the period depends on the initial conditions, okay? And so meaning that I'll get different periods as I change the initial conditions. So we've seen this before, solving for a pendulum as a function of drive amplitude or initial condition, and we'll do this in homework as well. Okay. Now, let's talk a little bit about chaotic motion. All right. So, nonlinearity and chaos are different. Okay. So all systems have to be nonlinear, but not all linear systems are chaotic. Okay, so in the chaotic system we're going to be looking at is a damp-driven pendulum. Okay, now a simple pendulum is a nonlinear system, but it's not a chaotic system. Okay, but the damp-driven pendulum is a chaotic system, so we're going to look at that particular system. Okay, so what distinguishes chaotic motion? I wrote down two properties. First of all, the long-term, or what I call steady-state behavior, is strongly dependent on the initial conditions. Okay, if I change initial conditions, the long-term behavior will be radically different. All right. Now, in the literature, this is known as the butterfly effect, meaning that something. Well, you can read the book, but anyhow, it means that small changes in initial conditions will drastically impact what happens in the long-term behavior of a system. Okay. The other thing is that this steady-state behavior, doesn't repeat itself. So if you look at the motion at long times, you won't see any, the motion doesn't repeat itself in a steady state. So a really better way of saying it, there is no steady state behavior. This thing is just doing a bunch of stuff. Okay. Now there is one confusion. People think that, well, since there is no rhyme or reason to that motion, it's just the motion's random. Okay, it's just some chaotic motion is random motion. That's wrong. Okay, chaotic motion is deterministic. What does that mean? Well, if I have one system and if I give that system the same initial conditions, it will exhibit the same chaotic motion. If I give it a little different conditions, it will exhibit a different chaotic motion. But that motion won't change. If I give the same initial conditions at one time and then do it another time, I won't get different motion. It's not random motion. So that's really important. Chaotic motion, it's deterministic, it's not random. Okay. So what system are we going to look at in class? We're going to look at a damp-driven pendulum, and this is my equation of motion I'm going to solve. Notice I have here, this is from F equals ma. This is my dampening term. Beta is my dampening term. This is my linear restoring, well, my nonlinear restoring force because it's a mega naught sine. And then I'm going to drive the system with a cosine. Okay. Now a couple things to note. Mega naught is a natural frequency. Okay. Beta is the dampening. Omega is the drive frequency. Okay. And then gamma is going to be some amplitude. If I set gamma equal to 0, then what's going to happen is there's not going to be any driving. Now, the two important terms in this is, well, it's going to be gamma and omega. And so I'm going to solve my equations numerically, and I'm going to set omega such a way that there's a natural drive period, and that natural drive period will be equal to 1 second. So what I can say is I'm going to say t, and that's going to be equal to 2 pi divided by omega. And I'm going to set mega, so that's equal to 1 second. That time period is going to set the time scale for my problem. Not omega naught. Why? Because remember, in a steady state, this stuff is I'm going to reach my particular solution, or my steady state solution is going to last. My transient solution is going to go to 0. Okay? And so really I'm interested in the steady state behavior. Now what am I going to do? I'm going to solve this differential equation in the steady state, okay, for different values of gamma. Okay? And I'm going to look at basically 8 cases in class. We're not going to do all that here. And I'm just going to change gamma, not by very much. And we're going to see very different behavior as I change gamma from 0.9 to 1.13. Okay. By the way, this should be here 0. I don't know why that didn't show up. 1.105. Okay. So the question is, how are we going to look at this behavior? All right. Now, again, I'm going to be changing gamma, which is the drive amplitude. The fundamental time scale is going to be TD, or big T, which is 2 pi divided by the drive frequency. And I define things so that's 1 second. And then when I solve my equations, okay, so I'm going to look in the steady state. And I'll show you in a minute that the steady state is going to start after 2 seconds. So the transients are going to die down after 2 seconds. And I'm going to look really far. I'm going to basically solve these equations numerically from 2 seconds to basically 60,000 seconds. So that's 60,000 periods of t. All right. How are we going to look at the motion? All right. Well, we're going to look at the motion in the ways we did before. We're going to plot the angle as a function of time. We're going to make phase-space plot diagrams. Okay. Then we're going to introduce 2 ways of looking at the motion, especially for the steady state conditions. Something called bifurcation diagram and something called a Poincare section. Okay. So let's take a look at the motion for phase space. Look at the phi as a function of time and space plot. And again, let's take a look at that. Okay, so here what I did, again, I have to solve this numerically. I'm using Runge-Kutta code to solve. And what I do is I set gamma equal to 0.9. And you take a look, you can see there's some oscillations here, but eventually I hit the steady state. And typically I'm going to hit the steady state after 2 seconds or really after 5 seconds. So the steady state behavior is from 5 to 25. Now if you notice, there's some transients here, but eventually after 5 seconds I have a steady state thing. It kind of looks like simple harmonic motion. It oscillates about 0. They look sinusoidal. Looks like there's one period here, and that's what I expect. I expect something that look fairly one period, something like simple harmonic motion. All right. And again, the period is determined by the drive frequency, not the natural frequency. The drive frequency is 1 second. Now what I do is I plot the steady state phase diagram. What is that? Well, I don't plot from the points from 0. I start from 5 seconds to 25 seconds. I plot that. And notice here I get a nice round shape. Now, from this round shape, you can tell that, hey, it's not a circle. Okay, so it's not simple harmonic motion. Remember, a phase space diagram for a simple harmonic motion should be a circle. This is circular. That means it repeats, but it's not a circle. Okay. Now, let's increase gamma, and let's look at something that's at period 2. Okay, where it's 2 periods. Okay, now, again, what I've done here is increase gamma from 0.9 to 1.078. And you can see, again, there's some transients. But you can see here that it goes high, low, high, low, high, low. So there's 2 periods. There's a time from this peak to this peak and this peak to this peak. That's what I'd call period 2. Now you see where the phase space diagram is really important, because I see these 2 periods. Here's one circle is 1 period. The other one is the 2nd period. And if you actually watch this as an animation, we'll show in class, I'll do this, then go out to the outer one, then back to the inner one and such. So from there, you can see very clearly 2 periods going on. Okay? Now, for this particular case, I have 1.081, and again, increasing gamma. Now, this is a little harder to see, but there's actually not 2 periods here, but 4 periods. And if you actually zoom in, you can see that there's actually 1, 2, 3, 4. There's actually 4 circles there. Okay, so that represents 4 periods, but it's really kind of hard to see the periods. You really have to zoom in and look at the periods. So, is there any other kind of way to look at the diagram, okay, in such a way to see this periodic behavior go from single period to 2 period to 4 periods? And the answer is yes, and that's this bifurcation diagram, okay. But before I show you the bifurcation diagram, let's take a look at a chaotic case, okay. Okay, so now what I did was I increased gamma to 1.105, and you can see it's hard to see it. There's some periodicity here, but they're not the same heights. And so here you can see, well, geez, I don't see any closed shape, not circles, but closed shapes. And again, I'm only solving for 25 seconds. So it's like, okay, well, let's solve for 10 times as long. Okay, so if I do that, that's right here. Holy cats, now you can see that, well, I'm not too sure if I'm seeing any periods here. And this is kind of filling in. I'm not getting close shapes. If I'm not getting close shapes, that means the motion is not periodic. Let's solve it for another 10 times more seconds. Let's do that. Okay, well, there's not much information here. I mean, you can see here that it doesn't look like I'm getting any no closed shapes. That means the motion is not repeating. So this is chaotic motion. Okay, again, it's not random. It's deterministic. But there is no steady state behavior. That's really what's going on. Now, you can see here that really when looking at this phase space diagram is being problematic. How can I look at periodic behavior at all if it's just all filling in? And how am I going to look at chaotic behavior in a little bit different ways? So let's take a look. So I like to introduce this concept of a bifurcation diagram. And the bifurcation diagram is a way to look at the periodicity of a function of the behavior of the oscillator. Okay, and this is how we're going to draw this diagram. I'm going to give you code to do this. So what you do is you pick a driving amplitude. And then what you do is that the oscillations have to occur at some multiple the primary time scale is t, okay, which is 2 pi divided by the drive frequency. So what I do is I take my waveform, my phi is a function of time, and I sample it at a rate of t. So t read a point, t read a point, t read a point. Okay. Then what I do is I plot for a gamma. I pick a gamma on the x-axis, and then on the y-axis I plot all these values of phi I get from doing that. If it's periodic, all those points will be at the same point. Notice in this case I have a periodic wave. If I sample here, I get that value. Sample here, I get that value. Sample there, I get that value. I would get the same value each time. It would be 1 point. Okay. If it's periodic, you get 1 point. If you have period 2, you get 2 points, because you would say, okay, I sampled this guy here, but then the next one would be period. If it goes down here, I would have that one, and up and down, up and down. Okay. If it's chaotic, I get a bunch of numbers everywhere. Okay. So let's take a look at the bifurcation diagram for this particular system. And I did this here. So what I'm plotting here is, this is gamma. I'm doing gamma from 1.06 to 1.09. And then on the y-axis is the angle I got when I sampled it at t. Okay. Now notice what happens here is that from 1.06 to 1.065, I get one line there. That means I have one period. But then once I go from here to here, notice it splits. That's called a bifurcation. It bifurcates. And then I have period 2. And later on, it bifurcates again. So here I have 1, 2, 3, 4. I have period 4 at this particular gamma here. At this particular gamma here, roughly 1.083 or something like that, I have 1, 2, 3, 4, 5, 6, 7, 8. I have period 8. And then you can see I have particular gammas, like say this, I've raised this gamma up right here. You notice that I just have a bunch of jumble of stuff. Okay. That's chaotic motion. Okay. But notice as I go further in gamma, see I have a bunch of jumble stuff. But then it comes out, hey, wait a minute, I have a gap there. What that shows is that I go from chaotic motion, I increase gamma, and then I go back to period 2, or a simple period, and then I go back to chaos. Okay, that's what's happening here. So this is what a bifurcation diagram tells me. It tells me the periodicity of the function. Okay. Now, when we really look at chaotic behavior, there is no steady state behavior. As I increase the time I do my simulation, I'm just going to fill this thing in. I don't really get a lot of information from the phase space diagram. So what I want to do is I want to get I want to be able to describe the chaotic motion in a little different way. And so what I'm going to do is I'm going to use a different kind of phase space diagram. And that phase space diagram is called the Poincare section. So the phase space diagrams, they fill in and I can't gain information from it. So what a Poincare section is basically a sampled phase space diagram. So what I do is I solve my differential equation over a really long time scale, from 2 seconds to 6,000 seconds. Now, you may say, well, geez, that must take a long time on your computer. You know, it takes about 30 minutes to do. Modern computers are amazing. Okay, so this doesn't take, how many points am I solving this for? I'm solving this over 600,000 points, okay, on my little laptop. So I'm not using a supercomputer to do this, okay? You can do this at home, and I'll give you the code. You can do this at home. Probably should even do it for a longer time, but what I do is I go from 2. And why do I start from 2? Because I want to get rid of the transients. All right, get rid of the transients. I go from 2 to 60,000 seconds. Then what I do is I take phi and phi dot, and I sample it at t, and then I make a plot, a phase space plot, of all those points where n is 1, 2, 3, all the way up to 60,000 of phi and phi dot, and then I make a phase space plot. Let's take a look at that phase space plot. But before I do that, let's talk about what the Poincare section will give me. If I do a Poincare section for a simple harmonic motion or something at period 1, I'll just get 1 point. Okay, that's not very interesting. Okay. And that's because when I sample that, I have the same angle and angular speed. Okay. So it's not useful for periodic motion. Poincare section is useful for chaotic motion. So what we're going to see is chaotic motion is going to produce what I call fractal images. These are images that have similar structure when you keep on zooming in. Okay, and we can see this fractal structure. So let me take a look. So this is a Poincare section of my oscillator. I cannot really describe why it looks like these wavy lines. Okay, but this is what I get. And what I want to do is I want to look at the fractal nature of this. So notice how these lines kind of like this, and there's a little gap there, and it kind of turns around. Let's zoom in at this point right there. Okay, I zoom in, and you can see here when I zoom in, I got more structure. There's some splitting. And then let's zoom in here. Okay, I'm going to zoom in right there. I zoom in there, and you can see that each one of those lines have even more structure. Okay. And now let's zoom in here. And you can see there, now you can see, well, I'm having less points. The reason why I have less points is because I had only so many points when I did my calculation. If I did my calculations for more time, I would get more points and see even more structure. The more points I have, the more I can zoom in. So you see this kind of fractal structure, and fractals are something associated with non-chaotic behavior. So that's my introduction. Okay, this is nonlinear dynamics, and chaos is a very rich topic. We're just barely digging into it. But I just want to give you a flavor of what's going on. We'll see you in class. Goodbye.